so this is number 2 on page 104. This is, fondly referred to as the golf ball problem. Not fondly. Okay, that was sarcasm. So we're told that this golf ball, somebody does a 301.5 meter drive. What we want to know is, at a 25-degree angle, by the way. What we are interested in is how high this gets at its maximum. So at top of flight, we'll call that delta y max. What's the maximum height that it achieves? So if we think about the problem conceptually first, we're looking really at two different things. We have all the information for the total flight path, how far it goes, the angle it launches at, but what we're interested in initially is just this half. And what we know is if we divide this motion into this motion and that motion, at that top of flight moment, there's a moment where the velocity on the y-axis becomes equal to 0. There's a moment where it stops and starts to fall. So we would tend to call that something like VFY at max. We make heavy use of subscripts here. And we know that for that moment it's equal to 0. So that gives us something to tie this motion to a point in space, to a point on its axis as it's moving. So if we list our x and y variables, we immediately create expressions for VIX and VIY. Cosine theta VI, sine theta VI. Okay, that's easy. Always do that, never solve for those. Like seriously, never solve for those, unless that's what you're being asked for. Keep those as expressions. So we know that, and we're interested, so let's think about just what we're interested on the y-axis for a minute. We're interested in delta y max. And we know that at that point of delta y max, we have a VFY at max. And we know that that's equal to 0. Terrible handwriting, sorry. And we also know that acceleration on the y is equal to negative 9.81 meters per second, same as it always is. Second squared, sorry. So we've got those 4 things. If we were just analyzing this, which in a way we are, that would be plenty. We've got VI, we've got VF, we've got delta y, and we've got AY. Those 4 things we can tie together. And we can tie together with which expression? VF squared equals VI squared plus 2a delta y. And of course we would say that this is VFY, VIY, and that's acceleration on the y, just to keep ourselves in order. Okay, great. So if we want to rearrange this to solve for delta y at max, and I'm going to write in at max, we can do it. So let me get rid of that so it doesn't look like it's a negative. Cut. VFY squared minus VIY squared divided by 2a equals delta y. Okay. And we know that this is 0, so it goes away. So we have negative VIY squared divided by 2a equals delta y. And now we can put in the expression that we have up here for VIY, and we end up with this. Negative of VI sine theta quantity squared over 2a equals delta y. So it looks like we're done. There's just one problem. What is it? We don't have VI. Gesundheit. So we have to build an expression for VI. And while we can handle this all on one axis to get an expression for VI, and I said to somebody else, it's kind of like a triangle again, where you have to have 2 of the 3 pieces of information to solve for it. You're going to have to connect the x and y axis in order to get an expression for VI. So if we go back to our variable list and we continue it a little bit, we know that there's no acceleration on the x. And we also have to look at the total flight path to build the expression for VI. So if we look at delta x total, I can't even write this, 301.5, we also have the delta y total. And this is why it's really important to use those subscripts, because otherwise you will screw yourself up and plug in the wrong delta y and it's bad. So what's delta y total for this little thing? 0. It's hit from the ground, it lands on the ground. It has a total delta y overall of 0. So if we have, and I'll highlight these in a different color, if we have VIY, AY, delta y, and we want to bridge over to the x-axis, of course we always use time as our bridge. We've got our old standby, delta x over VIX is equal to delta t. What equation can we use to connect those? It's the favorite, my favorite, delta y equals VIY delta t plus 1/2 a on the y delta t squared. Okay. So we know that this is 0 overall, and it might be helpful to write total there. So if that's 0, then this becomes negative VIY delta t equals 1/2 a delta t squared. Well, if we continue to plug in the expression for VIY, what do we have there? Negative of VI times sine theta times delta t equals 1/2 a delta t squared. We'll come back. Okay, so when we last left our physics heroes, we were here. So we knew that we could use this expression to get the delta y max, but we didn't have VI. So we're going to use all of this stuff that connects the axes to get the VI, to get an expression for VI. So let's solve this for VI first. That's the easy way to do it. So negative VI equals a delta t squared over 2 sine theta delta t. And then we can actually we can call this a -1, that negative sign. And then we have VI equals a delta t squared over -2 sine theta delta t. Okay, which allows us to cancel out the squared. So we have VI equals a delta t over -2 sine theta. Now what? Back to here and back to there. Back to our expression for delta t, which we can plug into there. So we'll do that together on the next page. There was a question quickly on the algebra of getting this negative off of the VI, off of that side. So here, what I did was I in essence said, okay, negative VI really means VI times -1. So I'm going to treat that negative sign as a -1, as something that the VI is multiplied by, which you don't have to do, but for me it makes it easier to not screw it up. So that means if I'm multiplying by a -1 here, to get rid of that, I would have to divide both sides by -1. So hence why the -1 goes to the denominator on the other side. Okay. Does that make sense?
Yeah.
It's a way of bookkeeping for me, because if I don't do that, I tend to really screw it up, and then, yeah, it's bad. It's my crutch. Okay, so not losing sight of the fact that this is what we're getting to. This is how we're going to solve for delta y max. I keep losing my max. We have an expression for VI that's almost complete. So we're going to sub in the expression that we have for delta t. So VI now equals a times the quantity delta x over vi x over negative 2 sine theta. Okay. What we save by waiting until we've rearranged it for vi to do our substitutions is we've saved a bunch of pain and hassle with lots of other things. So it's good that we eliminated that delta t squared first. It saves some algebra. Okay, so now we have to get the final expression here. Oh, I've screwed up. I have screwed up. Not terminally. I thought I saved work, but in fact I did not. Well, what did I do? Do you see what I did? Yeah, I've got a VI right back in the middle, so I still have to do the ugly algebra, and I didn't save myself any work. Darn it, I thought I saw something clever there. I didn't do it that way yesterday any of the 3 times I did it. So it's just algebra. Okay. If we want to do the algebra together, we can. I'm going to copy this to the next page. Okay. We'll do this algebra as sort of a sidebar. So again, pea-brain, love algebra, still make stupid mistakes. I tend to do every step in something like this, especially when I have a fraction on top of a fraction. I guarantee I will screw this up if I don't do every step. So here's the algebra I'm going to do. Negative 2 sine theta vi equals a, and then I'm going to multiply out that fraction, delta x over vi cosine theta. So I've got this. At this point, what can I do to rationalize this side? Multiply the other side. So that's right. I knew there was a squared in here somewhere, a square root in here somewhere. Okay, so I end up with negative 2 sine theta vi times vi cosine theta equals a delta x. In other words, vi squared. Okay, this isn't so bad. It's okay. It's just algebra, I swear. Okay, so I'll recopy that whole line. So I've got negative 2 sine theta vi squared cosine theta equals a delta x. Now it's a pretty easy solve for vi. Everything that's multiplied by vi, I divide both sides by. So we have vi squared equals a delta x over negative 2 sine theta cosine theta. Solving for vi now, pretty darn simple. Take a giant square root and get rid of that radical. Okay. Now we have an expression, I should clean that up, for vi. This expression we're going to take and we are going to stick it right back into there. So let's take this and this to another page. Okay, so we have negative vi squared sine squared theta over 2a equals delta y. At this point, all you're doing is putting this in there, which of course means the radical goes away because it's a square root and it's squared. So we have the negative of, and I'll go ahead and put it in there just because, to not skip a step, sine theta, cosine theta, that squared, divided by 2a equals delta y. There is no more simplification possible at this point. You are ready to plug.
What happens to the sine theta?
What do you mean?
Negative vi squared sine squared theta.
Oh gosh, I forgot it. I'm sorry. Jeez Louise, you got to keep me on my toes every second. There, sorry. Okay. I would recommend doing this problem a couple of times. It is. We're going to plug it in. Oh lordy, which means we have to go way, 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 way back to here. Of course, you're doing this all on one sheet of paper, you know. Things to remember. So I'm going to borrow this whole thing. Things to remember and places to screw up, and I got sloppy. Remember that in that expression for VI, this delta y is the delta y max. I guess that's really the only one, and we didn't have another delta x, so it's not a problem. But whenever we've got multiple distances that we're using, you need to make sure you're keeping those straight. Okay, so the negative of negative 9.81 meters per second squared times 301.5 meters, or that should be total, not max, sorry, divided by negative 2 sine, is it 25? Theta? Sine of 25, cosine of 25, squared, sine squared 25. Do you know why we write the sine squared 25 like that? Have you done that in math? If you write sine 25 squared, then it looks like you're taking the sine of 25 squared. You're not. You're taking the sine of 25 and squaring it. Okay, divided by 2 times negative 9.81 meters per second squared equals delta y.
I just have a quick question.
Yep. Yeah, and what's going to happen is, of course, this is going to cancel out that. So, you know, I wanted to show the step, but yes, when you're squaring the square root of something, it goes away. Okay, do you want me to recopy it one more time without the square root, without the radical, or are you good to plug in at this point? I mean, it's just calculator at this point. It is a big nested thing, so unless you're doing every single piece independently, there are lots of potential places for calculator error. Yes, sir. So if you're entering this on one of the TI-30 multi-views, there are two ways to do it. Your calculator will automatically give you parentheses after you enter sine, and if you're going to put it in as part of a full expression, you have to close those parentheses. So you can put the sine of 25 in parentheses and then square it, or what I typically do, especially if I'm hurrying, is I put in sine 25, I hit enter, that brings up the sine of 25, then I just hit squared, select it and hit squared, and that squares the answer to whatever I just got, and hit enter again, and you have sine squared 25. So that's the two ways to handle that. It looked like there was a minus sign in there. That was meters per second squared in very bad handwriting.